The Webb look is so far out that discovering light has been traveling for north of 13 billion years. At this point, the universe has been broadening, and consequently, the light has been reaching out for the most far-off universes. We're recalling in time almost to the Big Bang. The monstrosity of the universe could appear to be tremendous, yet every single bit of it began from what we suggest as the peculiarity. At this point, this is the way we could decipher the Big Bang theory. However, the James Webb Space Telescope, JWST, has uncovered critical secrets about the birth and development of the universe, leaving us confused. Lofty physicist Brian Cox has broadcasted that the important discoveries made by the JWST could really reshape how we interpret the universe as a whole. Join us as we delve into these new glorious revelations that promise to change our perception. The James Webb Space Telescope, named after the renowned NASA chief James E. Webb, stands as a miracle in current cosmic examination. This telescope represents an immense technological leap forward from its predecessor, the Hubble Space Telescope, resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST outperforms the capabilities of its messenger. It uses cutting-edge technology and a design optimized for focusing on the universe in surprising detail. Not like the Hubble, the JWST delivers clear and sharp pictures of faraway brilliant bodies, working primarily in the infrared range. This fascinating part allows it to penetrate galactic buildup and capture divine things that were previously hidden away from our view. With its beast 6.5-meter primary mirror made from 18 hexagonal segments, the JWST reduces the Hubble's reflector size, positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point, L2. It orbits the Sun in a state of harmony with Earth, ensuring a consistent and continuous perspective on the universe while investigating the farthest corners of space. It involves investigating light years, but it also includes a kind of time travel. The JWST uses infrared instruments to see superb objects and events dating back billions of years. The light emitted by these objects, due to the expanding universe, goes through a red shift, moving from the visible range to the infrared frequency or longer. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling scientists to study the formation of stars, research vast galaxy development, and examine exoplanet atmospheres. Its most recent historic discovery includes identifying an enormous mass of galactic systems at the edge of the observable universe. This finding challenges the validity of the theory of how things came to be, prompting a reassessment of our key cosmological assumptions. To better understand how we arrived at this point, we should take a brief journey through the history of space exploration. Early civilizations like the Greeks and Chinese laid the groundwork for understanding planetary development by observing heavenly bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. During the 20th century, Edwin Hubble, a pioneering astronomer, made groundbreaking discoveries in cosmology and observational space science. His observations revealed that distant nebulae were isolated universes far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were receding at higher rates, providing evidence for the universe's expansion. The post-World War II era in space exploration marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969, all crucial milestones. Fast forward to 1990 when the Hubble Space Telescope was launched, providing extraordinary clarity and revealing shocking insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope highlights the continuous evolution of how we interpret the universe. It revealed the vastness of space and reshaped fundamental ideas in astronomy. Take the Hubble Space Telescope, HST, for example. It captured the famous Pillars of Creation image in the Eagle Nebula, unveiling a star nursery shaped by massive clouds of gas and dust. Another significant achievement was the Hubble Deep Field, capturing countless galaxies in what seemed to be a void patch of space. The HST also investigated exoplanet atmospheres, identifying components like water and organic molecules in distant exoplanets, suggesting the possibility of habitable zones beyond our solar system. Following the study of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments solidified the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, astonishing the world with its monumental discoveries. Its successor, the James Webb Space Telescope, was launched to build upon the technological advances and lessons learned from Hubble, offering a model for how we might understand the universe's origins. Today, this understanding is explained by the prevailing theory of the universe's origin around 13.8 billion years ago. The universe began as a hot and dense singularity, rapidly expanding and leading to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the structures we observe today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges in its early days. Alternative models, like the steady-state theory, proposed a universe without a specific beginning, and concerns about evidence for the initial singularity, expansion, and observed anomalies arose. Many of these objections were addressed over time, with significant evidence coming from the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with technological advances, further supported the theory. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can peer through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light known to humankind and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, nebulae, and the formation of stars that are hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves stretch, causing a shift toward longer wavelengths, redshift. The JWST's infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its evolution. Dynamic events like black hole mergers or new starbirths primarily emit in the infrared range, further expanding the JWST's analytical capacity. The telescope can examine phenomena that would otherwise be hidden or undetectable. The JWST complements optical telescopes like Hubble by having enhanced sensitivity and the ability to detect infrared radiation. This allows it to peer deeper into space and delve further into galactic history, unveiling hidden cosmic wonders and providing a more comprehensive view of the universe's evolution. The JWST serves as our window into the early stages of astronomical development. Recently, it uncovered something so astonishing that it could prompt a re-evaluation of the entire cosmological model of the universe. We found massive collections of galaxies at the very edge of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, during the cosmic dawn. The surprising part is that we are uncertain how such massive structures formed so early in the universe's history. This discovery could lead us to reconsider how we understand the formation and evolution of galaxies in the early universe. Studying early galaxies is critical for unraveling the mysteries of cosmic origins. The JWST can provide insights into how galaxies, stars, and planetary systems emerged and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its primary limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by distant galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to investigate the early universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope represents a significant leap forward in observing galaxies from the universe's infancy. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. The JWST's revelations provide a unique opportunity to observe the universe as it existed in its earliest stages. The ability to study galaxies so far back in time, when the universe was still in its infancy, allows us to better understand how the cosmic structures we observe today came to be. By observing these ancient galaxies, we can also examine the conditions that led to the formation of the first stars, supernovae, and black holes.